Okay, today's June 18th, and I'm out on a geology drive-about with Professor Hardt from Odessa College, and we left really early this morning, so we've made it down to just south of Imperial, where there's this spring with some ancient sulfur water in it that's permeated the groundwater and is now being forced up to the surface. And this is a interesting spot. It's a real super kind of environmental disaster, and you can see out there. You want to explain this?
Yeah, sure. So whenever they did this about 30 years ago, they were drilling down through rock layers deep underground, and they pierced a layer of rock that was trapping water underneath of it. Now, at that depth, this water was under great pressure, but it could not reach the surface because this layer of rock was capping it, preventing it from moving upward. And so once the drill pierced through that rock layer, it allowed a passage for water to come up. And this water was unfortunately full of high amounts of sulfur. And so the water flows up and forms this spring, which we can see down there. And it started permeating the groundwater system and filling these fields, which poisoned the fields. You can't grow much in a poisoned field, and so they had to abandon them, which is very unfortunate.
If you're ever down near Imperial, you can just pull over and kind of see this, and it's pretty neat. I'll get the GoPro down kind of to ground level here. And you can see the crystals and stuff as they go. The water is not super hot, but it's warm at this point. And it's pretty much, even in the middle of winter time, it'll be that temperature. You can see there are a few like bulrushes and stuff that have kind of adapted to this. And our good old West Texas Bermuda grass can take a lot of salt and stuff, and it's kind of hanging on around the edges of this. But interesting area here. Okay, good morning from West Texas. Charlie and Justin? Josh.
No worries.
We're new friends. He's the professor of geology from Odessa College, and I'm taking him kind of on a little bit of a geology runabout today, showing him some of West Texas. Just giving him a briefest of overview, because that's about all you can get in a day. We're driving now. We just stopped at the Sulphur Lake right south of Imperial, and we're heading on down to Fort Stockton. We're going to stop up here in just a little ways. I want to show him where the ground is subsiding from a sinkhole. Awesome. And stuff. This is some more, and this is kind of an interesting place right here. We're not going to get out and do a lot of real stumping around and stuff, but they've actually had to scoot the highway over because the road just continues to drop off into this sinkhole.
Wow.
And as you can see right here.
Yeah. Oh yeah, look at that.
And so, anyway, I'd aim the GoPro out the window right now, but I just got it set up and running. But it's kind of a neat thing if you're driving from Imperial to Fort Stockton and you see where they've widened the road.
I can hold the picture I just took up to the camera.
Okay. And so it's pretty cool. Just thought throw that one in. It's kind of a bonus geology, collapsing salt domes and stuff.
Yeah, you get the same thing from utilizing the groundwater for irrigation too much. That's a big problem we're having in the Great Plains aquifer right now. It's being depleted at an alarming rate by agriculture. And the more we remove water out of the ground, the more pore spaces between the grains and rock are left empty. That's now full of empty air, and the weight of all the rock above it starts to press down on it and compresses. And all that extra space means that we start getting subsidence on the surface.
This is interesting right here. Supposedly what this is where years of mismanaging oil-filled water, and a lot of people don't think about the fact that one of the biggest problems with oil field is water. And because a lot of times, this oil was laid down in the bottoms of oceans and stuff, and a lot of the water is very salty and very high mineral.
Yeah.
That was an ancient salt dome. And mismanaging the water, they've dissolved a big chunk of the salt out of the salt dome. Yep. And now the ground is collapsing down into what used to be the salt dome. About some of the salt characteristics of salt out here. And I was just telling Professor that the salt up around Kermit has collapsed out, and they've left a big oily mess down there. And anyway, he's telling me about the Gulf of Mexico.
Yeah, so a huge reason why there's so much oil and gas production in the Gulf of Mexico is because a long time ago, the ocean, the shallow ocean that would eventually become the Gulf of Mexico, went through sequences of being cut off from the rest of the ocean, and so evaporating away and coming back. Now when it's evaporating away, all of the dissolved minerals in it recoalesce, okay? They remake themselves basically into new minerals, mostly gypsums and salts. We call these evaporate minerals, and they would settle on the bottom and make thick layers. And so after sequence after sequence after sequence of this evaporation cycle, you get really thick layers of salt and gypsum. And then cut to now, all that thick layer of salt has pushed itself upward through cracks in the rock to be near the surface. This is a behavior that salt and several other minerals have called plastic behavior. Under stress, it will deform itself into a new shape. In this case, as it pushes itself up through a crack in the overlying rock, it makes a sort of plume, kind of mushroom shape. We call this a salt dome. As oil and gas is migrating through the sedimentary rock around these salt domes, it ends up getting trapped on the edges of these domes because salt is impermeable to fluid. Oil and water cannot flow through it, and so the oil and gas is trapped on the edges of it. That's what we target in the Gulf of Mexico. They look for a salt dome, they find a nice pocket of oil around its edge, they drill down through the salt dome to get to it. This can be tricky, again, because salt deforms. So you have to really plan your drill hole to take that into account. Use materials that can handle that kind of pressure, the salt being moved from all sides, all of that sort of thing. And like with what happened back there, you have to be very careful about water intrusion. If water gets into your salt dome, it will start to dissolve your salts. And not only will that make your dome behave differently around your drill pipe, but you can end up with subsidence on the surface, like what we just saw back there. If you ever make your way to Louisiana, there's this location on the coast of Louisiana, not far from Lafayette. It's called Avery Island, and it's the top of a salt dome just poking its head up above the surface. Now it's got a layer of sedimentary rock on it, so you've got plants and such on there. It's not purely salt, but lots and lots of oil production sites around the edges of this island. An interesting fun fact, that's actually where they built the Tabasco factory.
I was going to say, some of those plants might be very spicy too.
Yes, that's where the Tabasco factory is.
A little town called New Iberia, if you want to find it on the map.
Exactly. And the reason why they put the Tabasco factory there is, well, there are a couple of reasons, but a really important one is because they can have easy access to a lot of salt. And salt is a major component of how they make Tabasco sauce. So fun fact for the day, right?
Okay. Interesting thing too about, I was listening to him talk about the Gulf of Mexico, and I just throw this in. One of the things that occurs, you know, is the Gulf. If you look at it, there's some pretty good sized rivers, like the Mississippi, for example, which is one of the largest drainages in North America, drains down into the Gulf. And as it does this, it carries a lot of organic matter with it. And as this organic matter settles down into the Gulf, it's trapped under a lot of pressure. And if you look up the thermodynamic properties of that, as the bacteria eat all this organic stuff, you get a lot of, you know, methane. But under those kind of pressures, it really can't go anywhere. So what you get is this stuff called methane anhydride, which just kind of coats the bottom of the ocean floor. Now, as sediment settles over this, it eventually will cover it up and stuff, and that'll be the gas fields of the future. That's kind of, you know, part of that whole same, you know, it's all still forming natural gas and oil down in there. That doesn't mean we don't need to conserve and that it's a finite resource, but it just means that geological processes are continuing on. And I talk to some people about that. They go, we're still making gas in the Gulf of Mexico. We don't need to do all these weird conservative things. Well, yeah, we're making it on geological timeline, if you want to address that.
Yeah, we use these terms like renewable and non-renewable resource. Well, truth be told, every resource that we use is, to one extent or another, renewable. Every metal that we utilize isn't truly used up and gone. It's just in a different substance or in a different product now. It's still part of the Earth. It's still in the Earth system. Ultimately, will return to the Earth and could theoretically be used in the future. Things like oil and gas are constantly being renewed because biological organisms are always in that process of living, dying, being buried, and converting into hydrocarbons. That process, though, in particular, takes tens of millions of years. So will all of these organics, which you just mentioned is being put in the Gulf of Mexico, will those be utilized by us? Definitely not. Could they be utilized by some theoretical person in 10 million years? Probably. Water's the same way. Everyone tends to think of water, particularly groundwater, as a non-renewable resource, and for the same reason. Technically, groundwater is always being renewed. However, it is not renewed at the same rate that we utilize it, which is why groundwater stewardship is a really important deal right now.
Okay, tell me your 2 big geology lessons.
All right. So one thing I like to tell my students is that if there's anything they should get out of my class, it's that they should never ever be ripped off by a countertop salesman or a gravestone salesman. Because people like to market countertop material all the time as granite. Well, is it really granite though? Because granite is made out of some real good stuff. Granite, rightfully so, has a reputation for being a hard rock. It's made out of minerals like quartz and feldspar, which are fairly substantially hard rocks on the Mohs hardness scale. But a lot of countertop salesmen will try to market you lesser stones and call them granite because they just kind of group every rock under the term granite, or they know better, but they don't expect you to. So take a geology class, learn what's granite and what's not, so you don't ever get ripped off like that. And then as far as gravestones go, a lot of people think marble gravestones are really pretty, and to be fair, they are. But marble is a very soft rock. It's only a 3 on our Mohs hardness scale of 1 through 10. And on top of that, it dissolves very easily in carbonic acid, which falls in the form of rain all the time. Marble gravestones will deteriorate extremely quickly. So, some important life lessons that you can learn from geology.
Okay, I told Josh that I was going to tell him a story about gravestones. So, as some of y'all know, I tried to hike the Mormon Pioneer Trail 3 years ago. Anyway, and so I started out in Nauvoo, Illinois, and started hiking towards Salt Lake City. And I'm going along, and as I would hit different spots along the way where there would be pioneer graves and stuff, a lot of them are marked, I would get to noticing that they're all made out of this red granite. And I can guarantee you there is no granite at all in Iowa. And I didn't see any in the parts of Nebraska I was going through. So they weren't getting this along the way, which is kind of weird because they were carrying literally sometimes, 90 pounds per person is all they were allowed to carry. Yeah. So I got to checking on this and found out it's the same reddish granite that the temple in Salt Lake City is made out of. And so what they were doing is they would get out to Salt Lake City, and then they would make a stone and they would travel back to mark their loved one's grave. And so they were hauling this tombstones from Utah all the way back into Iowa and Nebraska and stuff.
Wow.
Which was kind of, I thought was an interesting history thing. And I was like, why were these people going back and forth this much? Well, they would go back to get the next group of people that were traveling across, and they would act as guides. But when they would do this, they would bring this red granite stuff to make tombstones for their loved ones who had died when they crossed across.
Wow.
And so it's through knowing a little bit about granite that I was able to piece together that, hey, these people were actually coming back hundreds of miles in wagons and on foot and stuff to mark their loved ones' graves. And I just thought that was kind of a cool thing. And I thought I'd throw that in as a little geology story.
That is cool.
Okay, here we are at entering the Sierra Madera Astroblem. And I was just telling Josh about some of the flora. So of course, this is a mesquite tree right here. And a lot of times they have beans. These are honeybean mesquite trees. There's two types of mesquite trees. There's one that has a twisty bean. It's called a screw bean mesquite tree. And then the straight ones are honey beans. If you're ever lost in the desert, you can extract quite a bit of sugar just by boiling those things down. This is a creosote bush or a greasewood. They actually don't have a lot growing around the base of them and stuff like that because they poison the ground, so they're not competing with everybody for water. Okay, here's a member of the holly bush family. This is called an algerita, and you can get little berries off of this at some times of the year. And the pioneers out in this part of the world would ferment the berries and make algerita wine and stuff. I don't know what the proper name for these things are. My family always called these Christmas cactuses. They turn bright red and green at different times of the year and stuff like that. But they're one of the many types of cactuses. Now we're going to be driving a little bit, and this is one of the things. I think a lot of people think this arid desertous country is just devoid of life, but there's a lot of plant life, but it's highly adapted to its environment. And that's one of the things that makes this environment so fragile. It's the fact that if you start fluctuating it, these plants are so adapted to this arid, dry desert and stuff that they don't really adapt well to a lot of other, changes. The grass here has super deep roots. This is a type of grass called curly mesquite. And you can grow this in Odessa in your yard. It makes big clumps and stuff, but you can have a yard you don't have to water. And so we're gonna cruise a little ways up the road here. And you can see the juniper tree over there. The juniper tree is quite often called cedar trees by people in Texas, and they are not. They're juniper trees. They have the same, they're a member of the same family and everything. Now be careful walking through this grass. There's a lot of snakes in this part of the world. This is a blah blah tree. I have no idea. I don't remember what this is. I should know, but I don't.
Blah blah tree, it shall be known.
I'll put it on the video. This is a cat claw, also known as a wait a minute bush, because if you're hiking through these things, a lot of times they will grab hold of you and hang on. And Josh has found rocks.
I usually do.
So what are we looking at here?
Well, probably a limey stone. Without some tools, it's hard to tell. But around this area, I've also found some very salacious rock, what looks like kind of a rough chert. Kind of like a novaculite looking rock. Yeah, there's little pieces of gravel that are coming out of the rock like that have been previously rounded before being put into the rock. So lots of different things around here. Once I can see something in outcrop, it might be easier to tell what we're looking at.
Okay, let's load up and head to an outcrop.
Yeah, let's do it.
And so this is a pretty country, and it's a pretty time of the day to be out here. It's going to get really hot today. And right here's great adaptability. I don't know if this is going to show up real well on the GoPro, but covered in thorns. A little bit of thorny nastiness for your walking enjoyment. Okay, so on the Sierra Madera Astroblem, this is the rebound hill that's in the middle of it. Okay, we've stopped just north of Marathon, and we're at this very folded, bent, interesting geology place. And this is one of those that, when you look at it, there's bands of chert and stuff mixed in, and there's just some abrupt changes in geology, just where it's just bam, changes. You want to talk anything about this, or?
Yeah, it's very complicated what's going on here. So over here, we've got horizontal beds, largely horizontal beds of chert and some fine-grained rock that looks fissile, like shales, maybe like a limey shale stone, mudstone. And then right here in front of us, some of it is immediately turning vertical. Like it's doing this right here. So for example, this bed is horizontal all the way up until this point, and then it goes vertical like this, which is astonishing. You can see this this nice fissile material right here, this layer doing the same thing. And so you can see it cutting through those layers up there. So usually what will cause something like this is the incredible differential stress. We call it differential stress. That's when two forces are pushing against each other in two vectors, in two opposite vectors, okay? So towards each other, and so all the rocks caught between these two powerful forces only have two directions to go. right? If you bend a piece of paper like this, okay, if you're holding a piece of paper flat and you put both of your hands on two sides and you push them together, what's the paper going to do? It's going to fold up, right? And so that's the only place rocks can go. They're going to push upwards to make room for those forces. That's an important principle in geology. Rocks will deform perpendicular to the direction of stress applied. And so, since the direction of stress is in probably from these two directions, they moved upward. But the manner that they did it right here is really interesting to me. We're
Look at
seeing
this
it
over here.
Yeah, we're seeing it effectively in cross section lengthwise, instead of in cross section across, like slicing it down the middle. It's a really unique exposure of this situation. You're looking at all these layers head on vertically. Looks like they've all been tilted at almost, or even some of them maybe a little bit beyond 90 degrees. Almost overturned completely.
And by the way, I will tell you, I am, before anybody starts commenting about this, I am walking along here filming the rock, but I'm looking at the ground, so I'm not going to step on a long wiggly boy.
That's amazing.
This is almost worth the trip, wasn't it?
Right?
But this isn't near the best thing we're going to see today. So if you keep coming down this way, right, it continues with this basically nearly vertically turned bedding, and then switches abruptly. You know, I understand about pandemics, but when we find this kind of junk everywhere on the roadside, it's so disappointing.
Yeah.
You know, you put your masks in the trash can, don't chunk them out the window. Okay, and so as it's lifted up, it's pushed up deeper and deeper stuff. So we've had these bands of this wonderful black chert followed along by this. Oh, look, teddy bear choya. See, there's your teddy bear West Texas style.
Almost looks like a churro I wouldn't want to eat.
You said churro, it's choya. Okay, so now you get into more shale-like stuff here down on this end of it. And
Yeah, this is a solid layer of that fissile mudstone material.
anyway, ooh. Oh, that's cement.
Yeah. Man-made rock.
I always hate when you find something you go, oh, this is cool. Oh, this is man-made.
Yeah.
Okay, I will say this. You can, you know, as far as picking up rocks and stuff along the road here, I think you're allowed to. I should probably check on that.
Road cuts, yeah.
Road cuts, you are. Once we get further south and get into the national park, though, you are not allowed. So I'm always real careful how much rock I pick up. Ooh, that's a nice piece of chert.
Yeah, I'm liking this pale white shirt.
That's not from here.
It's falling out all over this
You think?
side. Yeah.
There's tons of that further south of here.
Unless someone randomly decided to drop a truckload of it here. I don't know where it's coming from.
But I'm always careful about how much picking up I do at this point, because we are entering the national park later on. And if the rangers find you with rocks, it doesn't matter if you tell them, I got this back up there by Marathon. You know, they will be tapping their foot and looking dubious at you. Okay, I'm going to throw in my non-expert geology, but usually when you find stuff that's this color, this denotes a presence of iron in the rock.
It is true.
And usually, a lot of times, the iron was put there organically. In other words, bacteria extracted it out of everything and settled it out. Yeah, there is a lot of that chert around here.
Yeah.
I'm going to mash this. Okay, so these rings right here, as we're looking at these rings, what causes those?
So a lot of the time in a marine depositional environment like this, what causes concentric rings of material are sponges growing on the bottom of the ocean, okay? Back in the way old days, right, our reefs weren't made out of coral like they are now. For most of Earth's history, reefs were made, the backbone of reefs were sponges or sponge-like animals. And so they would make large colonies growing layer upon layer upon layer. And so when we're looking at this bed tilted vertically, we're looking at it basically from the bottom upward. So we're looking at the oldest part of this individual bed here. We could be looking at what is essentially a sponge colony that is now being exfoliated from the bottom to the top. I've seen this in several other locations, and that's what it looks like to me.
So what causes the black chert?
Usually organic content. When you have black shales, when you have, well, I mean, look at oil. Oil is black. Why? Because it's full of organic content. It's that carbon. So black shales are full of carbon from organic material, and black chert often contains carbon from organic material as well.
So if I like go up and
yeah, it probably won't smell like shale will. It's not. Chert won't be holding oil or anything. It's
no, but I was just wondering if it might have any, and probably sitting out on this road cut, if it had volatile organics, those have already volatile away.
Possibly, but yeah, there won't be anything that you can burn. Just a little more carbon content.
So we're back down to where the curve up goes. And so this is the little more horizontal bedding. Look at, is this faulted? I can't tell what's happened here.
Let's see.
I don't know if that was done by human excavators or...
I mean, it could have been that, but it doesn't look like a fault.
Another one of these big circles.
Yeah, generally a fault will have some amount of offset. So where two layers, or one layer looks like it should connect to itself over a crack. Instead, you'll see it continue on the other side of that crack some distance, some vertical offset away.
We will show you some faults. I know where there's some faults at. This is interesting. This is one right here. See the?
Yeah, this is a tiny little one.
See the upset right there?
And you can actually also see, you see all this broken, kind of shattered material in there.
But you can see the layer up here that drops down almost a foot.
Right.
Look at all the calcite deposited in there and stuff. It's pretty interesting.
So as water percolates its way through the crack, it brings dissolved calcite with it, which turns into crystals in that fault crack. And it incorporates the pieces from both sides of the fault that have been scraped off as the fault is moving. We call that a fault breccia.
Okay.
This is a fun exposure.
Look up here. Here just all of a sudden switches from going up to going down. Look at this.
Yeah, this is tilted in the other direction.
Oh, and look how painted it is. I'll move up there where maybe that shows up a little better. The subtle coloring in here. But now we're looking at the tops of the beds rather than the bottoms.
Yep.
Okay. You ready to go see some more geology?
I think so.
Okay, we just left the marathon and we're coming up on a couple of low hills here that I want to pull over. This is part of a geological I lost the word. Anyway, this is the gap tank formation. Formation's what I'm looking for.
Formation, gotcha.
And anyhow, I'm gonna kind of pull past them and then circle around and come back. There's two road cuts here, and if you just drive by them, you think, well, that's just ugly old rock. It doesn't look like anything impressive at all. Okay. However, these are pretty cool. Okay, so we're gonna get out here and poke around. I was just talking to Josh and said when we get out this next time we need to start putting our hats on. I can't emphasize enough, if you're out in West Texas in the summer sun and you like your ears where they're not smoking hot burned, you need to put a hat on. Just flat out say that. Okay, here, let's leave it up.
Okay. Gap tanks, so crinoids, right?
Yep. Okay, so what this hill is here, if you get up on it and you start pecking around, is it's full of coral bits and crinoids. See, a lot of these things.
Yeah, that's a crinoid round right there. There's one right here.
Okay, so if you just pull up some of these clods right here and kind of sort of start sorting through them.
Call these fossilized Cheerios.
Yep.
So if you want to know what a crinoid is, think of a big tall flower, okay, where all these individual little chunks are piled on top of each other to make the stalk, right? Until finally at the very top, you've got this, what we call a calyx. It's basically where the main body of the animal is, and it has little tentacles that kind of sway in the tide and catch plankton and bring it down into the mouth to eat it. Now, back in the day when these animals were alive, these cranids were alive, these stalks made out of these little Cheerios were stuck to various objects, rocks or whatever, the bottom of the ocean. Today, crinoids are still alive, but they move. They are no longer stuck in one spot. They have adapted so that those little arms that they use for eating can also be used for locomotion. It's pretty amazing.
Up there's the mother lode of all of it.
Here's a nice big chunk of them right there. It's about 5
Yeah.
or 6 of them connected.
See, here's a big section of them. Now, I usually get the paleo pick and both rock pit hammers, and I stick them in and use them to stand on while I'm on this, so you slide down a lot. But if you look around, you can also find corals.
Well, this is Pennsylvanian, right?
Yes.
So they won't be coral. They'll in fact be an animal called a bryozoan, which closely resembles what we have coral today, but is actually a completely different family. It filled the same niche back then that corals do today.
Bryozoans?
Bryozoans, yes sir. Some green shirt.
Nice.
Yeah. There's some more green something up there. Something falling apart. Very cool. Oh yeah, look at those. Oh, those are big. I could have sworn I just saw something down
Right
here.
there. Right there.
Right, yeah, there's that, but I thought I saw something else. Fossils.
Here.
Oh, nice. Yes, this is bryozoan right here. This is called a lacy bryozoan. Its full name is actually fenestrate bryozoan. Kind of looks like a sail attached to a piece of coral, but again, different animals.
Okay, and this is called a sticky brine zone. I don't know what it's called.
A sticky brine zone.
It looks like a stick.
Why not? Why not? I mean, there are
Geologists, I will say, are a lot better at naming stuff than physicists. You know, physicists are the world's most lazy naming people there are. I'm going to call this particle a gluon because it glues everything together. And I have no imagination whatsoever as a physicist. Wow, look, I just got through doing this complex integration. And I figured out that this arbitrary constant is actually the speed of light. But I'm not going to change it. I'm just going to leave it as a c. So that the whole rest of the time, all the mathematicians are like, why would y'all use a variable c when you're doing integration? Rage problems for math people.
Yeah, right.
So what do you think? Isn't this pretty cool?
This is very cool.
And this is just kind of a... But, you know, you can take a bucket of this back and little kids love to dig through this stuff.
Heck, my students will love to dig through this. This reminds me of when I found my first fossil, actually. It was an older rock, Ordovician rock. But I was looking for about the same stuff. There were crinoids. Before I found any crinoids, though, I found a brachiopod. First ever fossil I ever picked up and found on my own was a brachiopod called Dystrophia clarksovalensis. It's in Ohio. Brachiopod's kind of like a clam, but a clam is a type of animal called a bivalve. They look slightly different.
Okay, there's some interesting stuff right here. Here, I'll show you the sticky brachiopod.
Or bryozoan.
Branzoan.
By sticky, do you mean it's a stick?
Yeah.
Yes.
No, it's a rock.
No, it's a stick. That's a piece of wood.
No, it isn't. Oh, you're right. Oh, I'm embarrassed all over the place.
No, it's okay. Easy mistake. Especially with something that looks like a stick that's actually a rock lying around.
Okay, for those of you who are in fitness, if you ever want to get a calf workout, you should try standing on this kind of stuff for a while you hunt for rocks, because this is a supreme calf workout. You can take and stuff your geology hammer down in the ground and then stand against it. One of the things you don't really get from looking at this is if you take and wash this, a lot of this is not just dirt, it's very small fossils. Okay, we're just south of Marathon. I'm going to get Josh to tell us about this chert bed right here.
All right, so about 92% of Earth's crust is made from what we call silicate minerals. What that means is that they're formed around a structure of one silicon element and 4 oxygen elements bonded together in a silicon tetrahedron. That forms the basic structure for all silicate minerals. When those minerals break down and bonds start to loosen up and a material goes from one state to another state, you get a whole bunch of dissociated ions. This is a process called weathering. And one of the things left behind when silicates weather are those silicon tetrahedrons. And those get carried away by the water system, groundwater or surface water, and end up getting deposited somewhere eventually. Some of it makes it out to the ocean and it gets incorporated into seashells. But a lot of it will actually be deposited into pore spaces in pre-existing rock. And when it does, it makes a very silica-rich rock, which eventually, once the silica becomes rich enough, it will turn into beds of chert, which is as hard as quartz because this is essentially microcrystalline quartz, tiny little microscopic crystals of quartz that have all been bound together. All of it from the previous weathering of other silicate minerals. So we get really thick beds like this.
Okay, I'm noticing there's... Okay, here comes my big confession. I'm colorblind, so...
Okay.
I'm noticing there's like white, kind of a... I'm gonna call it a grayish color.
Some of this is grayish, yeah.
What's that right there?
There's a big patch of gray right there, but there's orange as well. There's a lot of reds and oranges here.
Maybe khaki color, or is that the orange?
No, that's tan, yeah, tannish orange. You're not wrong there, okay.
Okay. I don't see the orange, so...
Well, orange to me, tan to you, it's about the same-ish.
Okay, as we walk along here, you can see interesting... Is this a... What is this?
That is also chert. There may have been something melts in there, or something could have... That looks like actually where the chert bed kind of fractured and kind of shattered, like a micro fault, I guess you could say. One here, one over there, where the two sides were kind of shifted against each other and kind of fractured a lot of quartz chunks and made this irregular, again, that word I used before, fault breccia. Shut this broken glass here.
Anyway, I thought we'd stop and look at this.
Yeah, pretty neat.
Here comes some crazy guy in a Jeep. I hope he observes my Jeep and doesn't run me over. He's got the fancy Jeep. He has 4 doors instead of 2 doors. That's okay, I like my Jeep. These road cuts are one of the things, if you're wanting to get your children interested in geology, or just you're interested in geology and you don't want to do a bunch of going out and excavating a bunch of stuff, the state of Texas has already done this free of charge. And so you can come out here and take advantage. Now, you have to be careful because sometimes when the state of Texas gets through doing their thing, they will have shattered it more than what it was naturally shattered. Because they're, you know, I mean, if you look at this, they probably had to use dynamite or something to get this to separate.
Yeah, so what you see on the surface expression, you kind of have to take with a grain of salt. Because it's probably not going to be exactly what it looks like under the surface. Not the bag.
Oh, it's just...
You don't want to. But I mean, you can get a good idea of what's going on further into the formation, right? Like something like this, that's a linear feature that will carry on into the formation. And the bedding planes, those are going to carry on into the formation.
And you'll notice that these bedding planes are pretty tilted. So besides all of this happening to it, this has been folded at some point in the past. Or tilted at least. I can tell you just as an observation, any geologist I've ever been out with, it doesn't matter how many degrees or how long they've been doing geology, they pick up every pretty rock.
Every single one.
Okay, we're gonna get back in the Jeep and we're gonna move forward. Okay, we're officially in the park, and we've just entered in past the ranger station. I'm gonna stop and drive up to Dagger's Flats. Okay, Josh and I are out by Dagger Flats, and we've been admiring this nice black sand. Look at that mudstone and stuff, and we've come across some intrusions that are kind of confusing Josh a little bit because they're pretty cool. And they're sills, is what he's saying, where they've flown between layers of limestone. We're walking back over here to look at some basalt right now. Ooh, Josh.
So here's another outcropping of them right here. Wow. Oh, look at the size of those amphiboles in there. Those are huge. Okay, let's keep going.
Look at this.
Yeah, there's some more of it. Oh, that's a plant.
I know. I was just seeing what it was.
And now in this one we're getting really big feldspar crystals. This is looking more and more like a diorite. More of it. This isn't basalt, this is more of that rock.
Look at this.
Yeah, it's chert with quartz crystals that had a little bit of room to grow on them. That's crazy. So at a distance, well, hold on.
I was going to say, hold on. Some of this back over here was good old Big Bend black basalt.
Going up here, I would say that this is dark enough to call basalt. But as we go downhill, we see an increase in the number of light silicate crystals.
So this,
and this is hard to classify because it's got a lot of dark silicates, but it's got a lot of light silicates too. I would call this a diorite. But up there are so few light silicates just a few feet away.
let's look over here real quick.
Okay, look, we've got some limestone here in this little creek bed. There's an animal den over there.
Yeah.
Let's not wake the neighbors.
Yeah, I don't know what that is, but probably has teeth.
Yeah.
Okay, this looks like the regular old basalt that you get.
It does. Let's see
But
what it
it's
looks
not
like
when you
up
get up close to it.
Color can be deceiving at a distance, right?
Yeah.
Yeah, no, this is our mystery rock. There's an outcropping of it right here.
Here, hold this and let me get a good macro picture of that.
And then, look at this one. This one, look at the size of the crystals in that. Here's a smaller version of it. And then as we move our way up the hill, the light crystals are almost entirely gone, leaving us nearly an entirely dark silicate mineral composition, which I would call basalt. Very interesting.
Some of the basalt is so hard down here, like see this. That's not, but some of the basalt down here is so hard it gets colloidal fracturing and everything.
All right. So we could be looking at two entirely different flows sitting on top of each other, like the basalt sitting on top of the diorite, or some kind of sequence of crystal loss. I'm going to see what I can see further up the hill. So there's this thing in geology called Bowen's reaction series. A scientist named N.L. Bowen discovered it, or established it, I should say, in the early 1900s. He did experiments to see which minerals would form first as a magma was cooling down. Yep, this is limestone on top of it, which means that this entire thing has been a sill. This is a direct contact between limestone on top and igneous rock underneath, which means that we were just walking through a sill. Okay. Looks like a sandy limestone. But Bowen's reaction series states the order in which minerals will form as temperature is decreasing. Just like all materials have different melting points, they also have different crystallization points. And so at, say, 1200 degrees Celsius, you'll form olivine, and then you'll form pyroxene, and then you'll form amphibole, so on and so forth, until finally you form quartz. Quartz is generally the last thing that forms. And so, through that, we know that you'll start off forming more dark silicate minerals early on in a magma's life, and more light silicate minerals at the end of a magma's life. So it's interesting to me that this one sill we just walked through, at the bottom,
Okay, we've been bouncing along some dirt road here. Not real bad. These aren't bad dirt roads. But we went up to Dagger Flats and we're coming back to the main part of the road. We decided we might cut our trip a little short rather than rush through the rest of Big Bend. We're gonna skip Terlingua today. We'll come back down some other day in the future. Okay, we're at the fossil exhibit, and I haven't been to the fossil exhibit with a geologist since they redid the thing. And so, anyway, see, 55 million years ago, large mammals.
yeah. That's cool. 130 million years.
Okay, I'm pretty sure my mic is picking that up, but there are some huge flies down here.
Yeah.
What is this? Is that a piece of petrified wood?
Yeah,
it is.
That is a tree.
Two of them.
Yeah.
Okay, I can remember when you'd come here and they just had the actual skeleton laid out of some big woolly rhinoceros or something they were digging up.
Echinoid.
Ammonites.
Yeah. The crinoids that we were finding earlier belong to the same classification of life as those echinoids. They all belong to Echinodermata.
Shark's teeth.
Yeah. Looks like some old mako. Zyphactinus. This Cretaceous interior seaway here. It went from what is now the Gulf of Mexico and split North America in half all the way up to Canada. That's what's responsible for the preservation of most of our best fossils in North America. Montana up there where I was before preserves a lot of fossils. Utah, Wyoming, the Nevadas, or the Dakotas. All of those.
Texas.
Texas, exactly. The museum I worked at during my undergrad internship has the first identified fossil of Teratophaneus curii, this dinosaur right here. James Jensen was the paleontologist that discovered it, and he was working out of that museum. Oh look, and this is a replica of the skull that we had at that museum. The exact skull, they copied it. It's cool. They used to think that it was a juvenile Tyrannosaurus, but...
I like the foot bones, metatarsals of all Tyrannosaurs are positioned closely together. This reduces stress and improves their ability. These metatarsals were discovered in the park.
Yep.
That's probably about all they found.
What's up? Dinosuchus. Love that picture. No, it's a Dinosuchus skull. Don't want to go for a swim in the lake with these guys.
Look, I'm riding the alligator. Mom, Dad, I'm riding the alligator. Oh, yay.
Plant fossils at Big Bend.
Palmetto. Coal. Allosaurus. Oh, did you get the Quetzalcoatlus on the ceiling over there?
Yeah. God, those were big. It'd be terrifying.
Yeah, largest flying reptile, the size of a small private aircraft.
Most common dinosaur at Big Bend.
What, Griposaurus? Oh, yeah, I see that. Interesting, most common. Sweet, well, let's go find some today. Bravoceratops. And the mammals.
This is what they were digging right near here.
It's a mean looking rhino, dude.
Yeah. Look at these jaws.
Woolly mammoth. Little horse. Harassotherium. Actually, that same museum I worked at with Teratophaneus has the original skeleton of this horse.
Mom.
Okay. So Josh, I'm looking over here and we see this wall of igneous material running up the side, and another one right here, and then back down here there's one. All of these are fanning out from the Chisos mountains here. Tell us about these.
Yeah. Okay, so these walls of reddish volcanic material that you can see cutting up and making these kind of wall-like structures through these hills, those are called dikes. And we call these discordant, intrusive bodies. What does that mean? So, sediment is laid down in layers, right? With oldest on bottom and newest on top. That's pretty standard knowledge. Imagine those layers as the pages of a book. And if I take a very sharp knife and I slice through the pages of those books, I now have an incision running top to bottom through all those pages, right? Imagine a dike as that knife, okay? It's made a slice. This magma is so hot that it cuts upward through perpendicular to these layers of rock, and it crystallizes there in that shape. That's what a dike is, and that's why it's making these ridges. It's forming the backbone of a lot of these hills here, because it's much more resistant to weathering than the sedimentary rock around it is. So we have a very clear one over there, another one next to it on the right, and then this one is, we are at an excellent angle to see this one head on, pointed right at us over there. Yeah.
There's White Jeep.
There's White Jeep.
Here's my friend Jennifer's favorite desert denzian, the cholla cactus. So, when I come across something like this, is this where they used to sacrifice Indian chieftains?
That looks like it.
These little cactuses, let me show you something. Almost missed this. If you're not careful when you're walking around out here, you'll miss these, and they can really mess you up because you think you're hitting a pile of grass. But see, this is a little ground cactus, and things got some pretty major thorns on them, and they're hooked. I don't know if you can see that. See the hook on the end of the thorn there? And so they will stab you with the straight hook thorns they've got, and then grab your socks with the other ones, and you pull pieces of it off, and they then end up planting it across the desert. And see, as desert life goes, every little crack in the rock has one of these. Pretty neat, huh?
Mm-hmm.
Got a really nice view here of a lot of different structures in the park. Wow, this is pretty. This little bush is called a cat claw. And believe me, these things have bled enough blood from me. They've got a little, it's kind of hard to see, but they have like a rose bush looking thorn right there. And if you're hiking around out in the desert, a lot of times they will grab you, particularly around the legs and stuff, and just shred you. Okay, this looks like granite to me, but it's not.
No.
Okay.
No, this is more of that cyanite.
This?
Same.
Okay, so you see the Santa Elena Canyon right there? This side of it's America, that side of that cliff is Mexico.
Really?
Okay, this is the Tuft Canyon. We're overlooking it right here. And tuft is a type of volcanic ash. And I can tell you, everything I thought I knew about Big Bend geology has kind of been flipped a little bit today, some of which I'm still not buying. But you can see this is where, you know, runoffs have cut through this tuff and kind of left it, you know, a little slot canyon. We're going to walk down into it. Greasewood, prickly boy. Look at that. Step on that, you think you've had problems. Another prickly boy. It's kind of a little short hike down here into the canyon. You get down in the bottom and it's like got gravel to walk through and stuff. It's so what are we looking at there on Castellon Peak?
That looks like some thick lava flows. And then underneath of it, there's sedimentary rock forming those more gentle slopes. That's differential weathering. Different rocks break down at different rates. A rock like a shale, for example, will break down and make a very gentle slope. A rock like sandstone will take a little more time to break down, so it will form an overhang on top of that slope. Limestone also takes a little while to break down, at least in a dry, arid environment like this. In a wet environment where it gets a lot of rain, it'll probably break down a little faster, but I think that's probably true of most materials. Volcanic rock is generally harder than sedimentary rock, so it will be more resistant. It'll form an overhang instead of a slope.
Explain all that.
All right, so this is our tuff here, all right? So tuff is microscopic silica blasted out from an explosive volcanic eruption. When it lands, it is so hot that it fuses together with other pieces of ash, as well as anything else that was thrown out of the volcano or that happened to be on the ground at the time. So we've got, you know, random pebbles in here that happen to be on the ground, but then we've also got shattered debris, stuff that was thrown out from our volcano. This is a big old chunk of basalt. And you can see all of these holes in there. We call that texture vesicular. Each one of those is called a vesicle. And if you look, some of them are actually filled in with what appears to be calcite. So in the past, water rich in calcium, probably from all the limestone around here, flowed through and filled up these voids with calcite crystals. And if you look up here, this shape, very distinct. It's got an aerodynamic shape right here. This is a lava bomb thrown out by a volcanic eruption, okay? See that teardrop shape? It's the same shape raindrops take as they fall through the air, right? Well, why do they take that shape? It is aerodynamic. And lava bombs do the same thing. They are pseudo-melted when they're thrown out of the volcano, and so they can take on a more streamlined shape before they crystallize.
That would imply eruption.
Right. Well, there's tuff, so there was definitely ash, which means that there was definitely eruptions in the past.
And I would not mess with any of those holes.
Oh yeah, no.
I have no idea what benzenes are in those, but they belong here and I don't.
There's a piece of granite right there, probably from a Pluton. It's got quartz, it's got feldspar. This is a lot of ash.
So what is this?
This is a silica-rich, it's like a silica-infused sedimentary rock. It still has bedding planes on it, deposition planes, but it looks like it's been filled with a lot of silica, probably from all the ash around here. Or it could have been washed into here. You found it on the ground, right?
Yeah.
All this stuff, like you said earlier,
It's
has no
out of context.
Yeah, so it could have come from up there, or it could have come from anywhere. But it's very hard enough that my steel on my knife wasn't able to scratch it. So that tells me it's probably full of silica. As water flows through this canyon, and as wind blows particles of sand and other debris through this canyon, it slowly weathers away, eats away at the bottom of the walls here, which is what makes this overhang. This is more basalt, but it's a different color, so it could come from a different event. This is so cool. Okay, so this basalt actually has pieces of other crystals in them, like little nodules of other crystals, like it incorporated them into it. That's pretty neat.
What's going on here?
Same thing. So these are pre-existing rocks, probably quartz or some other mineral. It's kind of hard to tell with some of these, and others have fallen out. But obviously they were incorporated into it before it crystallized. This looks like a big old chunk of our Tophaceous wall that fell out.
Yep.
You don't want to be standing around when that falls.
Nope. What's even better is it fell and then washed there.
Yeah, it's been rounded off, so it's definitely seen its fair share of floods in here.
Yeah, you sure don't want to be there when it's pushing that guy around.
Oh no. Look at this tree growing in the crack in the wall.
Life will go anywhere it can.
Right?
I'm going to re-ask that question.
Okay.
So, is some of this from pyroclastic flows?
So pyroclastic flows are a combination of incandescent ash and superheated gases traveling at about 125 kilometers an hour. And yeah, some of this is going to be deposit from pyroclastic flows, but the amount of ash expelled into the atmosphere from an explosive volcanic eruption, it's going to be settling down over the course of days and weeks. So a fair amount of this, like I would say most of all of this ash is probably going to be from atmospheric settling over time. Which is why you see bombs and such in there. The flows, that's going to bring debris. The bombs and all the stuff that was thrown up in the air, that's going to be atmospheric settling.
Anyway, that's Rio Grande Cane. Okay, so here we are at the river. Not much of a river right now.
The Rio Grande puddle.
Yeah, it's pretty silty. You can see the big old cliffs back there. We should build a wall on this side that's taller than that.
Yeah. That's the only answer.
Okay, this is the Santa Elena Rift, Rio Grande Rift. Tell us about it.
Well, the Rio Grande Rift is actually a lot bigger than the small part of it that we're seeing here. We're not seeing a whole lot of it here. That canyon was carved by the river itself, but the river flows in this direction because there is a what's called a rift valley slowly forming between the Gulf of Mexico and it's kind of going up into the U.S. Through where the Rio Grande River currently runs. And what that is it's a divergent plate boundary, so the United States, the North American plate, is actually pulling apart at that location along that valley. And as the crust gets thinner there, parts of the crust drop down to fill that space. And it creates this valley, and so the river runs along that. Eventually, the two halves will pull apart so completely that we'll start making a very thin oceanic crust, not a continental crust, between the two plates. And when that happens, the Gulf of Mexico will begin extending into the United States. Now this is going to take 20 to 30 million years, estimated, before we see that, but it's a process that is ongoing. The same thing is currently happening in East Africa with the East African Rift, slowly splitting that continent apart too.
Thank you, that's impressive.
It sure is.
Sure is beautiful. I'm kind of looking into the sun with the camera here, so I don't know what of the canyon you can see, but there's some shadow and the light's playing on it. I took some pictures. Okay, we're bouncing along here. It's still daylight, and we've left Santa Elena Canyon, and we've been doing this old Maverick Road for a ways, and this road is washboarded.
a little.
Anyway, we're oh, look how beautiful that is out that way.
Yeah, sunset.
But we've had a great time, learned a lot of science, got to see some gorgeous sights. Josh said this was the perfect day to go to Big Bend. I informed him that every day is a perfect day to go to Big Bend. But
Fair enough.
ooh, what is going on down here?
That giant area where it's been washed out, a lot of water action. It's probably a central point where all the water flows down into.
We go a huge drop off to the side.